In 1967, the British astronomer Jocelyn Bell Burnell identified a new type of object in radio observations she was making as part of her PhD thesis. This object emitted radio waves that arrive at Earth in regular pulses at about 1 second apart. The object became known as a pulsar. A pulsar is a neutron star that emits beams of radiation, radio waves, gamma rays, X-rays, and also visible light that sweep through the Earth's line of sight. Like a black hole or a simple neutron star, it is an endpoint to stellar evolution. The pulses of high-energy radiation we see from a pulsar are due to the misalignment of the neutron star's rotational and magnetic axis. Pulsars seem to pulse from our perspective because the rotation of the neutron star causes the beam of the radiation generated within the magnetic field to sweep in and out of our line of sight with a regular period, somewhat like the beam of light from a lighthouse. The stream of light is, in reality, a continuous, but to a distant observer, it seems to wink on and off at regular intervals. The pulses can occur from over 100 a second to 1 every 4 seconds. Because of the huge magnetic field and rapid rotation, strong electric fields are formed, also resulting in the mass emission of gamma particles, radiation, etc. In order for a star to become a white dwarf or a pulsar, after the supernova, the mass of the core must be less than 1.44 times the mass of the star. Otherwise, it will become a black hole. So far, about 1,800 pulsars have been found.
A supernova is an exploding star that can be billions of times brighter than the sun before gradually fading from view. Some supernovae are so bright they outshine whole galaxies. This explosion throws a giant cloud of gas, up to 10 times the mass of the sun, into space at speeds of up to 30,000 kilometers per second, about 1/10 of the speed of light. Supernovae are divided into two broad classes: Type 1, thermonuclear supernovae, and Type 2, core collapse supernovae. The class they fall into depends on the way in which they explode. Type 1 supernovae can be divided into three subgroups: 1A, 1B, and 1C, by differences in their spectra. The exact nature of the explosion mechanism in Type 1 is generally still uncertain, although 1A supernovae at least are thought to originate in binary system, consisting of a moderately massive star and a white dwarf. A binary system is a solar system with two stars, with material flowing from one star to another. In this case, material is transferred to the white dwarf from its larger companion. A thermonuclear explosion results if the flow of material is sufficient to raise the mass of the white dwarf above 1.44 solar masses. The white dwarf in a 1A supernova explosion is completely destroyed. Radioactive elements are formed, and the decay of these radioactive elements is thought to provide the energy for the supernova to shine so brightly. Type 1A supernovae are useful probes of the structure of the universe, since they all have the same lumosity. What this means is that the farther away a Type 1A supernova is from Earth, the dimmer it is, and the closer it is to Earth, the brighter it is. Lumosity is how much light a certain object gives off. By observing the red or blue shifts of Type 1A supernovae, we can calculate the expansion rate of the universe. When we think of a supernova, most of us think of a giant explosion in space. This classic explosion, associated with Type 2 supernovae, is an explosion of a supergiant, as big as at least 8 solar masses. Most supergiants are seen in spiral galaxies. Until now, the supergiant has shone brightly for millions of years, powered by nuclear fusion of hydrogen into helium, helium into carbon, and so on, until it has formed iron. Forming elements heavier than iron absorbs rather than produces energy, and since energy is no longer available, an iron core is built up at the center of the aging heavyweight star. When the iron core becomes too massive, the fusion that has been keeping the star alive slowly comes to a halt. So the gravity pulling the star inward is far larger than the explosive force of fusion that is pushing the star outward. As a result, gravity takes over and the core collapses, bringing in the outer layers of the star with it. These outer layers of gas, when they contract, hit the solid iron core and send a massive shockwave through the star, blowing off the outer layers. If the core's mass is less than about 3 solar masses, the collapse continues until the core reaches a point at which its constituent nuclei and free electrons are crushed together into a hard, rapidly spinning core. This core consists almost entirely of neutrons, which are compressed so much that the whole thing is only 20 kilometers across. This is called a neutron star, which can lead to pulsars. The supernova detonation occurs when material falls in from the outer layers of the star and then rebounds off the core, which has stopped collapsing and suddenly presents a hard surface to the infalling gases. The shockwave that this rebounding action creates goes through the star and blows off the star's outer gas layers. The amount of material blasted outwards depends on the star's original mass. A bigger star means more matter is blown off. If the core's mass exceeds 3 solar masses, the core collapse is too great to produce a neutron star. The imploding star is compressed into an even smaller and denser body, a black hole. Let me end on this. Supernovae are one of the most crucial aspects of space. Not only do they provide some explanation for quasars and pulsars, but they're one of the most important aspects of the universe itself. If it wasn't for supernovas, there would be no gold, no silver, no uranium, no element heavier than iron. If it wasn't for supernovae, you probably wouldn't exist, and we wouldn't be watching this video right now.
One of the most remarkable trends in gamma ray astronomy in recent years has been the emergence of high-energy gamma ray quasars, or quasi-stellar radio sources, as an important component of the gamma ray sky. Astronomers have since identified quasars as extremely bright regions that appear to get their energy from supermassive black holes in the centers of distant galaxies. When their gamma emissions are viewed through a telescope, these active galaxies are bright. Most of these sources are usually detected at high energies, 100 mega-electron volts or more. An electron volt is simply a unit of energy equal to approximately 1.6 times 10 to the negative 19th joules. It is the amount of energy gained or lost by the charge of a single electron moved across a potential difference of 1 volt. In fact, they have been detected over 1 giga-electron volts, and some up to several tera-electron volts. Given the large distances of these objects and the strong emission of high-energy gamma rays, these are the most powerful particle accelerators in the universe. Some appear as fuzzy stars and can be seen with large amateur telescopes. In 1963, the Dutch-born American astronomer Martin Schmidt identified the star-like objects now known as quasars. He showed that the spectra of quasars have huge redshifts, indicating that the spectra are produced by powerful energy sources in distant galaxies. Most of them are billions of light years away. Over 50 high-energy quasars are known at this time.